All right, just a quick check-in. Anthony, Alec, you're both good to go?
Yep. Can
All
you
right.
hear me?
Okay.
Yep.
All right. Whenever you're ready, Anthony.
Okay. Hello, my name is Anthony Abumrad.
My name is Joseph Howe.
My name is Alexander McGinnis.
And our project addressed the problem of autonomous recharging of aerial vehicles. Our faculty advisor was Dr. Nansung Wu. Our industry advisor was Dr. Polen Salam, and our client was K.R. Zentner of the University of Southern California. Next slide, and now to Joe, who will give an overview of our project.
So here's some images of our team, so you can put some names to faces. And then on the next slide, we have our overview. And so today we will discuss several things related to our project. In particular, the background, our proposed solution, our requirements, and the tests we use to verify our system performance, along with some administrative stuff. So next slide, and Anthony will now detail the background of our project.
So whether you work in tech or not, you've probably noticed that consumer drones are becoming more popular every year. And some of these unmanned aerial vehicles, which we'll refer to as UAVs for the rest of the presentation, are capable of performing automated tasks for commercial users as well, such as geographical surveying, small parcel delivery, and emergency response services. And these UAV systems have the potential to reduce the number of conventional service vehicles and delivery trucks from our roadways. And companies like Amazon and UPS are actively researching their capabilities for parcel deliveries in particular. However, battery life limitations continue to pose a significant challenge for long-haul operations. Next slide. Also, not every developer working on UAV systems has the budget of Amazon, and smaller organizations who are interested in researching these types of systems are typically constrained to small and low-cost UAVs like the ones depicted. These UAVs suffer from short flight times and limited features compared to their more expensive counterparts. They require frequent recharging or replacement of their onboard batteries, and this must typically be done by a nearby human operator. So what options do UAV developers have for addressing the problems of limited flight autonomy and short UAV battery lives? Next slide. These are a couple of the existing UAV systems we looked at. The top two photos depict a prototype system developed by UAV researchers at Kyungnam University in Korea. And their UAV payload included an infrared camera which tracked an icon on a moving ground vehicle. And this supports autonomous landing but not recharging. And depicted below is SkySense, which is a boutique UAV system which makes use of a grid of copper squares to provide connectionless recharging through a conductive UAV frame. And the system is designed for large UAVs, and it doesn't offer any autonomous landing, in addition to how expensive it is. So both of these systems are pretty impressive in their own right, but neither one is very accessible, nor do either of them offer both autonomous landing and wireless recharging. So we sought to implement an intelligent charging platform that could do just that for a small, low-cost UAV. Next slide. Our proposed charging platform provides wireless recharging capabilities and uses computer vision to issue the flight commands necessary for performing an autonomous landing of a small quadcopter UAV. Wherever possible, we designed the system with open source principles and component affordability in mind, and this was to ensure that our system could be accessible and adaptable by UAV developers with budgetary constraints similar to those we encounter as students. Next slide, and now to Alec, who will discuss our project requirements.
Here is a full list of our marketing requirements. For brevity, we would like to highlight key requirements. Next slide. Here are our most important marketing requirements. We emphasize the ability to land precisely using an upward-facing camera attached to the charging platform. The operating environment of our system was restricted to an indoor environment with typical office lighting. Finally, a PC should be able to connect and have full access to the landing platform. Next slide. Here's a full list of our engineering requirements. For brevity, we would like to highlight some key requirements of our implementation, and later in our presentation, we will discuss the revisions that were made to ER4 and ER6 of our engineering requirements. Next slide. The key marketing requirements were refined into the following ERs. We defined our necessary landing accuracy was a 5-centimeter radius. After a revision of our project in 2020, the UAV now has a required flight time of 3 minutes and a shorter landing sequence. The charging platform must be able to detect the UAV within a 2-meter cone in specific lighting, and the charging platform single board computer must accept an SSH connection. Next slide, and now to Anthony for our overview.
The charging platform is equipped with an onboard digital camera, for which we chose the OpenMV Camera H7, a single board computer, for which we selected the Raspberry Pi 3, a 5-volt power bank, and a wireless charging pad, which is specified to the QI standard of inductive coil charging, and that's QI spelled QI. Our system is paired to a BitCraze CrazyFly 2.1, which is depicted on the right, and that's a small, low-cost electric quadcopter, which natively supports programmatic flight controls and inductive coil charging with the QI standard. And this small UAV also satisfied our need to perform all of our development testing in a constrained indoor environment without posing any safety hazards to ourselves or our classmates. And an external Linux PC is depicted here to demonstrate that this was used to configure the software on the Raspberry Pi computer and run diagnostic tests. The Raspberry Pi computer communicates with and delivers flight commands to the CrazyFly UAV through the use of a 2.4 gigahertz ISM band radio module. Next slide. This is a 3D model of our charging platform and its key system components. So within a sturdy wooden frame, we designed 3D printed PLA mounts, which were to ensure that the focal plane of the digital camera and the top of the wireless charging pad were both flush with the surface of the enclosure. And this was to ensure that we could perform an adequate mathematical transformation of the UAV's position in the camera frame to real world coordinates. And Joe will discuss this in just a moment. Next slide. Here's a nearly complete assembly of the charging platform. Unfortunately, recent campus closures have prevented us from making some final touches to the platform, such as making a cutout for the wireless charger in the lid of the enclosure. Next slide, and now to Alec, who will discuss our custom PCB design.
The CrazyFly quadcopter platform can only accept one expansion deck by design. For our purposes, we needed it to have the QI wireless charging expansion deck and the flow sensor deck attached at the same time. To accomplish this, we had to design an expansion PCB, and we also included a high-power infrared LED driver circuit so that we could track the UAV with 2 IR beacons. This custom PCB allowed us to outfit the UAV with all necessary components without making permanent modifications to the CrazyFly. Next slide, and now to Joe for our operating model.
So we constructed a basic operating model for the UAV position with respect to the target landing point. And this model was the basis for a software control algorithm which processed real-time visual feedback from a digital camera to generate UAV flight commands. The XY positional errors are reduced to acceptable levels, and the UAV is instructed to land over the target point. The UAV set points are determined by the current distance of the UAV from the designated landing point. And this distance is then given back to the UAV so that it is able to make a movement closer to the target point. Next slide. This flowchart was derived from the operating model, and once connected to the UAV, the charging platform instructs the UAV to begin its flight path. While along that routine, the charging platform is checking the battery until a low signal is detected. At this point, the charging platform takes directional control of the UAV and attempts to center it over the charging point. Once centered, the UAV is instructed to reduce height. The ideal case for our model supports a single XY positional displacement followed by a single Z positional displacement, but hardware prevented this case. As such, we implemented an iterative model that slowly reduced height and frequently corrected XY displacement. Next slide. As mentioned before, the XY dimensions are reduced to acceptable levels, and this is accomplished by converting pixel coordinates from the OpenMV camera into world coordinates via mathematical transform. The Raspberry Pi takes into account the sensor size, active sensors, camera focal length, and object height to transform pixel coordinates received over a serial connection to usable coordinates in the world frame. These coordinates are then determined to be on target by making use of a logarithmic function solved for the acceptable coordinate area. In practice, this provides a horn structure of acceptable accuracy, which tapers over the charging point, and this allowed for improper detection of both beacons at high altitudes, as well as other hardware-related faults. Next slide. As the OpenMV camera is unable to natively determine angle with only 2 IR beacons, a mathematical model is used to correct for angle differences between the UAV and world coordinate frames. As calculating a vast array of vectors can be troublesome in the software, the angle of the difference vector with respect to the world frame x-axis is calculated. And this provides an angle that can be used to modify world coordinates such that the end UAV coordinates are as expected by the Raspberry Pi. This angle calculation occurs after every movement, and while this is potentially unnecessary if the angles are slight, it allows us to handle edge cases where the UAV has other hardware faults, such as improper movements or objects passing beneath sensors that can cause the UAV PID controller to have extreme responses. Next slide, and Alec will now discuss our test plan.
Here's an overview of our tests and their results, but we will highlight some key tests in greater detail momentarily. The test numbers define whether it is a functional test, FT, on a singular component or function, or whether it is a system test, ST, on performance of the system overall. The numerals refer to the test's relevant marketing requirement, engineering requirement, and index with respect to other tests pertaining to the same set of requirements. The tests marked in yellow will be discussed in the challenges section. Next slide. This is the rest of our test overview. Next slide, and now to Joe for our test results.
So to assess the capabilities of the system, we tested how accurately the software could guide the UAV to the target charging point. During each test, the software landed the UAV from a known distance, height, and angle, and the majority of the landings were within 5 centimeter radius, which is our engineering goal. However, due to hardware inconsistencies on takeoff, the UAV angle became slightly different than the expected angle, which caused a final movement to be erroneous. And the landing algorithm attempts to correct, as previously discussed, but by determining the actual and expected end positions, but it's only partially successful, as you can see from our figures. Next slide. Alec will now talk about the camera detection.
4 different machine vision UAV tracking techniques were tested: RGB LED detection, April tag detection, frame differencing, and IR beacon tracking. All of these techniques were implemented using the OpenMV platform. Frame differencing performed quite well, with no visual markers on the UAV necessary. However, it was extremely sensitive to other objects moving in the frame. Finally, we decided on IR beacon tracking, as it excelled in virtually all criteria. The only downside about IR tracking method was that it did not provide exact orientation information, like the April tag method would. Next slide, and now to Anthony.
We performed multiple power consumption tests for our charging platform components, which have been summarized here. The power consumption of each component at peak performance was measured for at least 25 minutes with a USB power sensor that samples every second. And by peak performance, I mean that the OpenMV camera was tested while actively running an image detection program. The Qi wireless charging pad was tested while actively recharging the UAV, and the Raspberry Pi was tested while performing a Prime 95 stress test. We strive for our charging platform to consume no more than 25 watts and to be capable of at least 4 hours of continuous operation. And we found that the aggregate power requirement of our platform components was just under 5.5 watts on average. We also designed some custom power switching PCBs that would allow the Raspberry Pi to switch off the power to the other components during non-use. And so this 5.5 watt figure is a conservative estimate for long-term operation. We initially planned to test the system battery life explicitly by connecting all of our components to our battery pack and operating until system failure. However, we had already exhausted our allocated project funds and made a judgment that it was not worth the risk of damaging our one and only 5-volt battery pack by loading it to failure for multiple test trials. The manufacturer specs for the energy storage of this battery pack suggests that it may supply the power requirements of our charging pad for up to 24 hours, but this is fairly optimistic, and without independent testing, we're not assuming that this is a proper specification for our system. So at the moment, we can't provide hard specifications on the battery life of our platform, but we can reasonably expect it to last much longer than our 4-hour target. Next slide.
So as any UAV does not have unlimited battery, the overall time it takes to land is crucial to the successful deployment of any system such as ours. To this end, we timed the landing sequence of the UAV over multiple runs with both the detection algorithms that showed promise. As Alec mentioned previously, the infrared LED detection algorithm proved superior. This was also true when considering the landing time. In terms of the Crazy Fly 2.17 minute flight time, the frame differencing algorithm takes around 37% of the total flight time, while the infrared LED algorithm takes around 9%. However, this does not take into account our added hardware, which further reduces the overall flight time of the UAV. And so this also makes the infrared LED detection scheme all the more appealing because we have a lower flight time overall. Next slide.
So I'm going to highlight some notable hardware challenges we encountered. As expected, we needed plenty of spare propellers, motors, and other UAV parts to replace those broken by crash landings. And while the Crazy Fly quadcopter and its parts are relatively affordable, these costs definitely add up. As Alec mentioned earlier in our presentation, we developed a custom PCB for the Crazy Fly, upon which the infrared LED circuit was implemented and to which both the flight sensor deck and Qi wireless charging deck could be attached. Unfortunately, the combined weight of these boards was almost double the maximum payload recommended by the UAV manufacturer. And sure enough, we struggled to reliably achieve liftoff and maintain control of the UAV until we were able to identify an affordable set of performance motors that could be directly substituted for the stock motors. All that said, the combined impacts of increased weight, high performance motors, and a high-powered infrared LED driver circuit meant that there was a much greater power load placed on the UAV's small LiPo battery. And this required us to revise our specifications of the expected flight time from 5 minutes to 3 minutes, as previously mentioned. However, in a few minutes, I'll discuss an ongoing design improvement to address this shortcoming. And I previously mentioned our decision to forego a time to failure test for the system's 5-volt power bank. But one other notable shortcoming was that nearly all of our UAV batteries were showing signs of failure by the time we had completed our custom PCB. And this has prevented us from gathering adequate data points to assess the UAV's wireless recharge time with the new hardware. So our system's performance with respect to our engineering requirement 4 is currently inconclusive. And now to Alec for some further discussion of our software development challenges.
We also encountered many software challenges we had to overcome. The landing algorithm on the charging platform consumed many man hours of development. The prototype code that was developed in December used 3 different threads and a simple direct pixel-based navigation, which could not accept real space coordinates. This implementation was scrapped completely in 2020 and rewritten with numerous improvements, including a more organized and object-oriented design. The visual tracking method was also a major challenge that had to be overcome. Numerous different methods were extensively developed and then later scrapped. A long time was spent on the RGB method, as promising results were obtained from prior projects. However, false positives are largely what prevented these techniques from being effective. OpenCV April tag detection was also explored for its attractive, precise 3D rotation tracking. However, the resolution of low-cost cameras limited April tag detection to unacceptably low altitudes. The frame differencing method seemed promising during testing. However, overwhelming false positives caused unforeseen errors, which prevented the takeoff during the January presentation. When the IR method was completed, which unfortunately did not happen until after quarantine, it proved to be far superior to any other, as it provides highly precise tracking with virtually no false positives. It has also significantly reduced average landing times from over 2 minutes down to 40 seconds. Next slide. Here's a very broad overview of the schedule for our project. Research and planning, as well as system build, went quite smoothly. However, when the parts all came together, several unforeseen hardware changes meant that we had to repeat several time-consuming tests, which caused the system build and performance testing stages to take longer than anticipated. Next slide. Here is the itemized budget for the project. Some parts were purchased with separate funding that is not included here, including additional Crazy Fly platforms. These extra parts were not included because they were used for exploratory purposes and did not make it into the final product. Next slide, and now to Joe for our video demonstration.
So here's a very quick video demonstration of a landing from start to finish. And so when considering our designated requirements and necessary specification alterations, we have achieved the goal of autonomously landing and recharging a small UAV on a designated charging platform. As mentioned previously, though, some of our data in regards to the charge time is not sufficient to really give a hard specification, but we at least accomplished the goal. And so next slide to future works.
So during the campus closures, we actually completed a second iteration of the Expansion PCB. And this new version is a smaller and lighter PCB that still provides the same functionality of our current design. Further testing, as we've mentioned, is still required. And there's also the potential to adapt our system for use with other unmanned vehicles. Next slide, and now to Alec for closing statements.
Here is a list of our supporting courses. Next slide. Here's our references. Next slide. Here's the rest of our references. And here we would like to acknowledge the Correct Foundation and the SSU Office of Research and Sponsored Programs for providing funding. Next slide. We are now ready for questions.
Okay, great. Thank you. Thank you very much. Just a quick note that after this Q&A, you will get to hear from Department Chair Dr. Farid Rahman and our EE Program Industry Advisor, Mr. Chris Stewart. So hope you can stick around for that. Now, time for questions. And I see Casey. Please go ahead.
Thank you. This is an interesting project. So I'm an optics guy, so I'm curious about your optical system. So first question is, what was the wavelength of the LED sensor? And I noticed that you had a IR bandpass filter on your focal plane. So if you could talk about the wavelengths, and then how do you think this would work if there was path loss due to clouds or something like that, and perhaps talk about the how you would achieve contrast with direct overhead sunlight.
So we used 940 nanometers, and the bandpass filter we used was glass, and I think it had a half width maximum of 20 nanometers or something like that. And this system was scoped to only operate indoors. We filter out the 940 nanometers from overhead indoor lighting by lowering the exposure. It will not work under sunlight because we can't filter out the sun.
To build on that though, frame differencing doesn't have the same problem with sunlight as IR does, so that is a potential option. You just have to deal with the fact that the landing times are going to be a lot longer, so that could be a potential adaptation.
And drone researchers are using their systems indoors, which was our target market. So that's why the scope was indoors.
Okay. Next question from Ali.
Yes, your project, your presentation and demo, they're all excellent, really, very good. And I want to ask you now, do you have any plan to, market this thing, basically share this thing with some of the other, the funders and so on, and go forward?
I can take that one. Yes, our client is in fact, and unfortunately we forgot to mention this, but our client is a fellow researcher as well, and at a lab in Southern California. And so our goal was really to create a system that could be easily picked up. And since we used mainly off-the-shelf components and all of our code is open source, a person could reasonably expect to purchase all the components themselves and build this system from scratch. We would, of course, be willing to help them in any way they needed, but everything's freely available, so they can use it. And if they have any questions, we are available to answer anything we can. And future iterations as well, we're going to try to keep working on the smaller aspects of it that kind of limited us in terms of weight. I see Chris Stewart has his hand up.
Yeah, so just a quick before we do Chris, just a quick reminder to complete the evaluation form for this group and all other groups. If you haven't done that, what you see on the screen is the link to the evaluation form. And now, Chris, go ahead, please.
Great job, guys. A very challenging project to take on, so good job getting that to work. Just wanted to pipe in and ask my standard question. So I'm going to kind of get a feedback from all you guys on what's the most important thing you learned through the process. And I like what other people have done, right? What would you share with the incoming seniors for next year?
I'll start off by saying that probably the thing that gave us the greatest amount of grief was not considering some of the challenges outside of the electrical engineering domain. So as I mentioned, the whole issue with creating a PCB that surpassed the recommended payload of the quadcopter that we chose. This was just not something that three electric, circuit-minded individuals really thought about in advance. We were concerned with, does our PCB, it passes all of our electrical tests, so let's slap it on and get this thing flying. And sure enough, that was not good enough. So consideration of mechanical challenges and just kind of like thinking outside of the schematic, so to speak. That was a big one.
And I will echo what other people have said about time management. For the most part, we were pretty on time. We were running maybe a week behind on some cases, but it was most of the time delay came from the challenges we encountered. So those were unfortunately unexpected. The thing that I experienced personally was I got a surprise internship this semester. So the time I thought I was going to have to devote to really working out these bugs evaporated pretty rapidly. So I would say anybody who thinks they have a good handle on what their time's going to be, double it. And then if they're still kind of not sure, triple it just in case, because things will come up. You will have personal things that will interfere.
And I would say I learned that bigger drones are always better. And also you don't know the problems you're going to run into until you start building.
Yeah, that's a good thing to mention as well, is try to build early, try to prototype early. You won't have the problems that we encountered, which was we built things pretty much when we started building things a little bit later than we had thought. And so they kind of snowballed on us in terms of the challenges that piled up.
Okay, very nice. I think we have time for one more question, and question from Neil. Neil, go ahead.
Yes, hello. So very nice to see the project and to get the little video at the end of it. You mentioned that you were doing this as part of a wider research project working with people, and I noticed you're using github.io on your website presentation. Did you manage to capture all your moving parts, the software and the PCB designs on GitHub, or is that something you think might be valuable? Just anyway, something just about how do you capture your current context to pass it on to somebody else?
That's actually a really good thing. I was realizing when we were starting the presentation that our GitHub repo probably needs updating with some of the hardware aspects of our project. And we could probably put a full bill of materials on there as well to really inform people who are looking. And so in general, we still need to do some work and just kind of tidying up the last little bits of our documentation so that anybody who's looking at it doesn't have to watch this presentation and read our full engineering report to understand what we did. They could just, pull down the code, look at all of our diagrams and build it for themselves and get on with whatever testing they wanted to do. So it is something that we do need to consider, and it'll probably be done this weekend.
Okay, so I'm hearing that you did put some up there, because in an initial view, and I haven't dug into it deeper, I couldn't find any links to.
Oh, I'm sorry. The website itself might not have it.
Could you post the link on in the chat, please? That may be helpful.
Sure.
But it was just a comment there that I was kind of digging into it, and but thank you very much.
I'm glad somebody was interested enough to look at the code.